All right, morning everybody. Sorry for a bit of a delay this morning. Right. So maybe we'll go back to where we were last time, and which was we were talking about. So we were talking about the non-abelian stable envelopes, and in particular, we were talking about non-abelian stable envelopes for quotients by a product of general linear groups. And an example of that is the Hilbert scheme of points. So we had this particular example here. So we need so this is symbolic for some cohomology class, or by cohomology class I mean cohomology class or K-theory class, or elliptic cohomology class. So this is try to get it to work. So this is symbolic for this alpha here. This is cohomology class. Cohomology class for Hilb C2. Well, in this case, 4 points, and then we would need to manufacture from it a symmetric function of 4 arguments. And so the way to do it is you take the R matrix between your space, that is in this case the Hilbert scheme of points, and then an auxiliary space you choose. Well, in this case you get 4 copies of the Fock space, and then the matrix element we will take. Which matrix element we'll take? We'll take, well, the matrix element we want here, and then the vacuum in the other channel, and then on the other side we would like to have a vacuum. Here's the vacuum in our space. Is vacuum in auxiliary space, and this is the vacuum in, so to speak, physical space. Physical means the space of interest, and auxiliary means auxiliary. And so then we take so this remains to specify one thing, which is the matrix element in this corner here that we would like to take. And what I say, well, let's take the following. So we're taking n copies of the Fock space. This is like shifts of rank n, and among all shifts of rank n there's one particular one, namely where all the boxes sit at the origin. That is to say, all the x and y, or whatever, however you're going to call it, x and y are the operators, they correspond to loop. They're all 0. So these are the quiver. This loops means these loops here, they're both equal to 0. All these things. So this sits at the origin, and then there's one box in every framing, so to speak. One box corresponding to every framing means the framing maps. So what does it mean here? It means here maybe. So what does it mean? We have some space, our subspace V, which has dimension 4, and some space W, which has dimension 4. Here I have, all right, both with dimension 4. Both dimension V equals dimension W equal to 4. And then here I have my loop maps, which is, so these are both vanish. This map is an isomorphism, because this means this is a quotient. Since this is a quotient of the trivial sheaf, so this, okay, that's subject. And then the maps the other way Map the other way is 0. This vanishes by moment map. Map equation. And then here, in this space, I have my framing variables acting x1, x2, x3, x4. So this point is an equivariant cohomology class. And then I have this group action here. And so this I record that group action is, so that is the group. So this is an element. So via the isomorphism between V and W, this element here, this becomes an element of GLV, which is right. So a class on the stack. I mean, stack is somehow there's not much geometry to the stack. A class on the stack is basically well, I mean, basically like a grand K3 class or whatever, a grand cohomology class on the point of the group. So it's a class function on the group. And so these are the elements in which you investigate. So maybe this was an exercise. It was as an exercise I asked you to think what it says for what it says for Grassmannian. So raise your hand if you did that exercise. All right, so maybe I'll proceed with the solution. So what would it mean for Grassmannian? For Grassmannian, so for Grassmannian, do I have a copy of this thing? Yeah. So let me copy this thing here again. So now for x equals T star of Grassmannian K plane in n-dimensional space. What do I want that here? So this is a quotient. This is a quotient by GLK, right? And so we need symmetric function in k variables. I need a symmetric function in x1 through xk. So what we're going to do here? Here we will take. So this is the evaluation representation for the Grassmannian. There is only one, and so we'll take that C2 of x I goes from 1 to k. And so this is what this representation is the cohomology also the Grassmannian, but of we take this joint union over all maybe L going from 0 to k T star Grassmannian LK, and then the analog of the star here. So what would be the analog of? So maybe I'll leave the star here, and I put the other graphical representation which I had here. So let me take it from here. So what is that? That is the space. This is supposed to be the space or it's a point really. So this is the point where what happens? Where the framing, the space V is actually isomorphic to the framing space, i.e., and all other Krug maps are 0. I.e., in the sum here we have the T star of Grassmannian KK. It's an element that appears here, and that is a point. Right? So this really is a point, and so that in the conventional language, we're taking the so in the conventional language, we're taking the matrix element between some. So let's say if our vacuum in our physical space, this is Grassmannian Kn. So let's say vacuum means we have all spins down. Let's say this, take this vacuum, this n spins going down. Right? Then here is our class alpha. Our class alpha sits in the Grassmannian of k-dimensional spaces in n-dimensional space. So this could be, for example, could be represented by k of them being up, k of the spins being up. So maybe let's say, something like that. So there's k spins up. Out of. So then here we have k spins down. And then here is, so this is kind of like this. It's like the Grassmannian. Maybe I'll put the. So this is about T star Grassmannian of zero-dimensional subspaces in k-dimensional space. This is about T star Grassmannian of zero-dimensional subspaces n-dimensional space. This is about T star Grassmannian of k-dimensional subspace and n-dimensional space. And then here we take the T star. This is going to be about T star Grassmannian of k-dimensional subspace and k-dimensional space. So these are all spins up. We'll put them in the red since they go up. And so then what we recognize is the very, very, very classical, and each of these lines has its own. So maybe let me draw since there are 4 of them. Draw the 4th of them here. So each of them has its own variable, x1, x2, x3, x4. And so we realize a very, very classical formula, namely, so what is this? Matrix element of the R matrix acting in the auxiliary space. It's some operator in R space. And so if we read this diagram backwards, what we see here so here we're trying to destroy the state labeled alpha, but instead we can read backwards and think about creating a state. So reading backwards, we get expression b of x1, b of x2, b of x3, b of x4 applied to vacuum, where this is the operator the operator that goes from spin up on one side, spin down. So there's in the Yangian or the quantum group or whatever associated to SL2, there are 4 operators corresponding to 4 possible. So you can on 2 sides of your transfer matrix you can have whatever. So on the 2 sides you can have spin up or down, and so these are the, and this one is whatever creates is usually called B, and so that is that's very classical form. So it's like the first, the main, the first and main form. Formula of algebraic beta ansatz. So this is the one for the Yangian of SL2 or UH bar of SL2 head, maybe GL2. UH bar of GL2 head, so forth. So, and then the general case, in the general case, the main difference, so this is general case. Case differs from this one by the fact that I stick in a kind of very special point. Here, this point has a concrete description, but here is the special point. Maybe I can characterize this point by saying that, well, each Wi is isomorphic to Vi, corresponding Vi, or the other way around, depending on stability. All other maps here. 0. Well, this is, or the opposite map is the isomorphism, depending on stability. And then the very general statement we can prove along these lines is the following. So this is general prescription how to do algebraic beta ansatz for anything that's related to quotients by GL, by products of GL. So let me then discuss the general setup. The general setup is that X is an algebraic symplectic reduction of some space. So this 4 lines means algebraic symplectic reduction. Well, let's just take one GL, since or products of GL BI. So these are the okay. Well, let's not complicate matters by indices. And so, what does this mean? This means that that if I have a Z, remind you that I have a Z, then inside there's a locus, which I think we denote Y, which is the pre-image of the 0 under the moment map. Well, inside Y, there's a stable locus. Well, strictly speaking, we let's exclude the situation where we have a strictly semi-stable point. Let's have a while stable, and then this projects to X. This is a quotient by the group G. And that's the statement. And now the constructions that we consider here are the following. We introduce this space, which is Z twiddle. That is Z cross T star of home. And let me denote the space V prime. So this is this is the framing space, but I emphasized, but what I did emphasize, but this is the framing space, but it is of dimension v equals dim v, and in fact we will be interested in the case when they will be in fact isomorphic on the locus that we care about. So since it's isomorphic, I decided to denote it W prime, V prime, and then what about that? So then I claim that we can. So then there is also similarly to here. Here there is an extra action. There is an action of the group the whole GLV prime, and then inside that group maybe we'll choose one particular group, just the scalars, 1 times u times u times the LCV prime. So these are scalars. So that would be, this would be particularly important for us. And so then this this, if I look at the fixed locus, so then the fixed locus Z prime of we look at the fixed locus of U. Well, what that includes, like for instance, there is your original Z cross 0. It also includes it also includes the fixed locus. So then if I look, it also includes things like if I take the locus of the scalar. So maybe this means the scalars you take, maybe to be pedantic, let's have it U prime, and then corresponding U would be U times 1 V. That would be a subgroup in GLV. And so then if I have a fixed locus of that cross the locus where V prime is isomorphic to V, and then the other map is 0. The cotangent line, that map is 0. So this is 0. That's clear. So because if I have a map, if this is an isomorphism, that if I act by scalars in V prime, I can undo this by action in V. And then this is maybe if I take, maybe if I take Z prime, Z twiddle reduction 1 GLV, then this would be exactly right. So if I take this quotient, and if now I take the action, the fixed locus of U, that would be there's this reduction by GLV, and there's similarly here. maybe let me take a stack. So sorry. I should have. Let's take the stack, and then that would be exactly right. Or G is chills. Right, so this is where we start, and this is where we end from our perspective. And so now get my, since I started confusing myself. Let me look at my notes, and then we can then, so that I don't have to. Right. Right. So then we can consider. So once we have that Z, so maybe this was slightly premature to introduce that talk about fixed point. Let's have X twiddle. Let's have X twiddle to be let's denote, well, X. So let's have the Y twiddle to be the pre-image under the twiddle map of 0. So this is where, so this from the home I get, that is that twiddle map is whatever it was before plus AB, where I have V going to V. So this may be A, and this is the map B. Okay. And then I similarly define X twiddle to be Y stable mod JV. GLV. And then so inside and then about the stable part, there's kind of an important point that any point, well, if our stability condition is such that, well, it depends on the stability condition, but which we choose for GLV. So at any point where, so if where I guess I was losing everyone for a minute. Sorry, I think we're back to being online and recorded. Some glitch in Zoom. So what we're planning to do? So we're planning to take the we will take sorry. So this is we were maybe to reconnect. I'm explaining a general framework that encompasses the construction that we did for the quiver varieties at the beginning of the lecture. And so now, so this is what I did is I had some space Z, maybe with an action of GLV, and I'd like to construct this non-abelian stable envelopes for that GLV. And then the way to do it, I said this is going to be reduced to usual stable envelopes. Now for a billion group action on some associated space. That associated space is where I consider, kind of add the framing. Means I take T star from, so I get another copy of V, maybe call it V prime. Take T star of home from V prime to V. This has an action of V prime. And now, so this will be the space Z with the tilde. And then, so then I have the corresponding moment map, which is this. Is the moment map for well, maybe I don't have to underline twice for the space Z tilde, and then a corresponding locus Y tilde and corresponding space X tilde, right? And so then what lies in that space is the locus, in particular was the stable, is the locus where this map from V prime to V is an isomorphism. Okay. So now what we will do is we'll take so we take on that space X tilde here. We have an action of GLV prime. For this action, we take stable envelope for this U prime. This is in the center. It's a subgroup in the center of GLV prime. And so in particular, that stable envelope is invariant. Under GLV prime, because stable envelope canonical elements, they commute with the equivariant, sorry. G prime, right? So then what we can do is we can take so this is so that's stable envelope. So now what we'll do, so stable envelope, what this has, this is on the quotient. This is on the quotient by G. But then on the other hand, it's some object on the quotient by the group G, but it's equivalent under the other group. And so then what we can do is we can lift it to the pre-quotient by one group and descend it to the quotient by the other, right? That makes sense. And so in particular, we'll lift. So first we will lift to Y y tilde stable. So it's some object, it's a cohomology class or K3 class or elliptic class on the quotient by the group G, and we can lift it to the stable. Then we can restrict it to y iso. So what is y iso? This is the locus. This is the locus. This is the locus where the space V to V, that space is an isomorphism, and we decided that by direct analysis, that's all such points are stable. So they all sit in here on this set where this space is, where this is an isomorphism. Clearly, if this space is an isomorphism we precompose with GLV, then of course here GLV prime here it acts freely because it's an isomorphism, and so we precompose, it's a free action, and so then one can descend to the action to y twiddle isomorphism quotient by GLV prime. So what we did is we had an action by quotient by one group and the action of the other, and we traded it for quotient by the other group and the action of the one. But since we're on the locus, somehow not much is happening. We're on the locus where where the two spaces isomorphic, and so there's somehow very little happening here. But it is so this axis in the auxiliary space, they start out as being framing variables, but then they end up being an element in the group we want. So that's how exactly it's happening here. Because we fix an isomorphism, so the action of two groups becomes the same. And so now, what now we will have, so now, well, remember that non-abelian stable envelope was about extending a class from y stable to z. That was the point of that. But now we have a class. We have something that lives here. But now I'll take that z and I embed it in here. And how that's supposed to go? So z. So I have a map, point z, and it has to go to this y twiddle mod isomorphism mod GLV prime, right? So this is what's the coordinate here? The coordinate here, this is, when we take mod GLV prime, what do we get? We take the T star home from V prime to V, and then mod GLV prime, so maybe isomorphism. And we take it mod GLV prime. What do we get here? Here we have a map, maybe call it A, and A is an isomorphism. And then we have the map B going the other way, B. So this is when we. So what's the quotient? If this map is an isomorphism, it's already free action, and so the only coordinate, the coordinate on this quotient is precisely AB, which is in a home from V to V, right? So that's exactly the coordinate. Okay? And so then we need to go from some point. So recall that the map. This is the set where mu inverse equals to 0, and then where mu tilde is to 0, where mu tilde is whatever I had mu before plus precisely AB. So this embedding is just sets AB to be minus the mu. Right? That's the embedding. That makes sense. So we get one more coordinate and we get one more equation, and we can exactly satisfy this equation by choosing the coordinate appropriately. That makes sense. So this is the embedding, and so then so then we take the stable envelope of some class alpha is, we decide this is restriction of whatever the class, you take the whatever stable envelope with respect to this GLV action. This is of some class alpha. What we would like it to be? We would like it to take the stable envelope of, with respect to that U of this class alpha. This is in. So what's the chain of transformation? We take the stable envelope on that space X twiddle with respect to U of this class alpha, because this is X. X was one of the components. X is a component of X U, X twiddle U. So it makes sense of this. Then we take lift with respect to GLV. Since the quotient we can lift, then we descend with respect to, then we restrict to this isolocus, then we descend with respect to GLV prime, and then we pull back with respect to this map. That's okay. And so the only thing you need to check is that it is really supported where it's supposed to support. It needs to be. So this is it's very easy to check that is the section of the right bundle, and then you need to check that it is supported on actual mu inverse of 0. But and the way to check it, well, we know it's supported. Well, how do we know this? So it's supported on mu twiddle equal to 0, where mu twiddle is mu plus AB. On the other hand, AB is this part AB here. This is invariant with respect to U. It's some coordinate on our space, which is invariant with respect to U, and vanishes on X inside X twiddle, because X is embedded by both A and B is 0. And so therefore A times B equals 0 on the whole U attracting manifold. So we have some invariant function, which is U corresponds to scalar matrices. AB is action of U on AB is a commutation, which is trivial action. And so if I have some coordinate which was 0 at the beginning, and I take attracting manifold, and that coordinate is invariant, that coordinate still has to be 0. So this is the whole trivial attracting manifold. This is 0, and therefore, in fact, the fact that this is supported here, this is equivalent. So this is equivalent. So this follows. Sorry. This follows from being supported. Attracting manifold. So that's the end of the proof. I'm sorry, it took me forever, especially with this technical interruption. But anyway, we got to this. Any questions about that? What I said? All right. Well, anyway, there's a you can there's a so there's a reference for this argument. It's this paper about beta eigenfunctions. Right. So now today we will so this leftover from last time. I'm sorry it took me almost an hour to fill that leftover, but anyway, this is. And so now we have we would like to compare. So now the topic today is that this vertex with descendant. So I think we did something like that. So vertex with descendants. I claim that this is in fact equal to this non-abelian. So this connects K of X and Kc of the stack, and this is the Chern character. So this thing is that the Chern character applied to non-abelian elliptic stable. When normalized correctly, and we'll explain this in a second. So there is this action there's this action. By the way this is defined, we have use the action of Q on the domain of the map, and then this elliptic curve would be C star mod Q. And so let's unravel what the statement says. So this is that's the topic for today. Well, whatever, next topic. So what does the statement say? First of all, there's a map. So we have first point is that we have a map from C star to C star mod Q, which is the elliptic curve. So I have a map of curves that induces the map of groups. So this induces the map from equivariant K series. K theory is the theory associated to the curve C star. So then it induces the map from equivariant K theory of any space X, the spec of that. There is a map to the spec of equivariant K theory elliptic, the same group, elliptic, the same equivariant, the same space X. So then for maps the other way, this is pullback, so we have a sheaves go here. The sheaves pullback. So elliptic homology classes, K-series classes, there are well, sections of some sheaves or some line bands homogeneous some sheaves on certain schemes, the spectra of the corresponding homology theories. So they go back here, and so that object here we will denote by that pullback. We'll denote by churn character. So this is why it's denoted by churn character, is because that this is somehow this is really an abbreviation. So it should be this denoted by the churn character is really abbreviation from the usual churn character. The usual churn character is when you have a map C going to C star, which well depends on how you denote it. Maybe you take this exponential, right? So when you take, so this means when you had then when we talk about the usual churn character, when we have a K-theory class, we think of this as exponential of cohomology classes. We pull back under this map, and so that's the usual churn character. And then similarly, but corresponds to the maps between the underlying curves. And then if I have, and here I'm going to use this map, and so in principle should be used. We should use, what we really should use is write instead of churn, we would like, churn kind of K to E, maybe pull back, something like that. But that's just too long. But this is too long. And then second thing about this, well, this can't be really right because this is some more like a hypergeometric function. This is more like a hypergeometric function. It doesn't looks nothing like elliptic function, really. I mean, if you think about it, it's a hypergeometric function. How can a hypergeometric function be an elliptic function? Then this is the way you understand is that first of all there is, so maybe I'll write kind of, so So if you'd like to have a comparison, then we need to have a formal to have an equality, to have an actual equality. Sorry, not approximate, an actual equality. We need one. So this is one. This is we use suitable gamma factors. Gamma function factors. That's second. And then interpretation. So it's interpretation of weak sense, kind of. Meaning you pair the vertex. Means you don't think of this as a class. It means we pair the vertex. We have a vertex, and we maybe pair it. So let's call it, maybe think is alpha, and then there's the vertex, and then there's beta. So this is really key. So this is we choose. So it's an element in a covariant K-theory of the stack. We choose insertions, and then we pair them. And so then this is really a pairing, because otherwise it's not so. Then we can talk about, then this is now a function, and then we can talk about two functions being equal. So this is all variables, and we can talk about two functions that actually being equal, right? So so what's then the statement? The statement, I recall that we have our x, maybe to summarize this. So what does it mean? Maybe equivariant. That would be maybe more. So we have some x. X is the algebraic symplectic reduction of some space Z by the group G. And then we have a group G. Forgive me for using the twiddle again, but this, let's call it twiddle. So there's a twiddle subgroup G, and then there's some quotient, maybe called the automorphism quotient. So this is when we talk about equivariance on X, we have respect on this group. So this is X on X. And so then we have the K, I have the following, so there will be the following diagram. So this is really a theorem now. So will be the following diagram. We have K equivariance, that means with respect to this group of automorphisms of X. So then, and then we need to make it, it will be a statement about meromorphic functions. So this means I write it Z and meromorphic. So it means I extend the scalar. So this means, so I'll explain this. It means I extend the functions to also include Z and Q. So this thing doesn't have Z or Q in it. So then here with Z and Q in meromorphic functions, I can use the Chern character of elliptic stable envelope for the group G. And then I go to the stack time. So this goes to the K-theory, G equivariant K-theory of the stack. Right? So that's Similarly, with Z and meromorphic, then here I use some multiplication by gamma classes, which I'll explain in a second. Multiplication by gamma function. This is like a Q analog over a tiny map. It's like a Q analog of a tiny map. And then here I have the actual vertex with descendants. And then this then go to the stack. And here slightly different gamma. And also it's twisted by like h bar to the power minus dimension x over 4. But never mind that. Okay. So now what is that meromorphic stuff? Is that k g x z mero means I take meromorphic functions on what? On spec kgx cross take a unit q less than 1, so I give myself q, and I also give some toric variety. Toric complexity. Well, since I'm talking about meromorphic function, maybe it's not so important, but so maybe I'll take the z. This is peak x o times c star. This is where that variable z lives. Okay. So I have to give myself more variables, and this is how I do it. And then they're analytic in Z in a neighborhood of, so to speak, 0. 0 here is some point at the boundary of that. So this corresponds to a stability condition. Maybe this is slightly parasitic. Maybe we don't, for the statement we don't need that stuff. Okay, that's the statement. And so what does it mean in a weak sense? In a weak sense, that means that if I take my vertex with descendants, so I have some class alpha and beta, then what I have here, this is, well, that's some kind of integral on the stack. So this means I can pull back and push forward on the stack. So this means it's a pairing between class alpha and there are some gamma functions. Basically stop beta on some gamma functions on the stack. The pairing on the stack is just an integral, so it's an integral over maybe 1 over the while group. So let's say, and then the integral over all x's are absolute value 1, and then dxj over 2 pi I xi, and then you put your class of alpha of x, and then stub beta of x, and then there's a gamma over gamma, this sort of thing. And then if we compare it, so if we compare it with the formulas we had last time, so last time we had formulas of the kind that if I take k-theoretic stable envelope, sub k-theory of alpha, and maybe divided by some denominator, and beta, that is the same as I take alpha, take a relative condition, beta, and this is a formula from last time. And then if we use this formula here, what do we get here? But this is the fundamental solution of the Q difference equation. And then this will be saying, so corollary becomes that this, if I take alpha, this fundamental solution, and then beta, take a matrix element of the fundamental solution, then this is going to be 1 over the order of the Weil group, this integral over xi equals 1, then there's the Haar measure of the variables xi. And then what do I integrate? I integrate, maybe call it f alpha of x, g beta of x, and then ratio of gamma over gamma. This denominator gets eaten up as, so we discussed that this denominator, that's, kind of, this denominator here becomes part of that expression here. It cancels with something. That denominator gamma will, we'll talk about this gammas in a second. This gamma have to do with, well, think about it in a second. And we spoke about it last time, so maybe we will not emphasize it here. But so this is, so where this is the elliptic stable envelope of beta, and this is the k-theoretic stable envelope of alpha. And what's the difference with last time? The main difference with last time is that this is, so last time we had an almost identical formula, except this object was not there. And instead of this, there was some contour here. So this would be place to some contour. That depends on stability condition. Okay. So maybe first a philosophical remark. So if I have so in Q different situation, this is to have a elliptic function in the q-difference integral, this is like a choice of contour of integration, because this is a constant. So this object here, so these are, first thing I want to claim is these two objects here, this interchangeable. In the words, difference equation. Meaning, suppose I have a Riemann integral, and then I can either specify the domain of integration, or I can affect that domain of integration by choosing some weight functions, right? That's especially true in the q-difference situation, where, since I'm interested in the solutions of q-difference equations, if I put a elliptic function, that in fact, from the point of view of my equation, that's like a constant. So it means it's like I put like a constant in the integral. And of course, if I put a constant in the integral and I have an integral, but the constant it's like a constant that is free to be different on different contours of integration. So it's like, suppose you have some basis of contours of integration, and then you put a different constant in different places. So that would be saying, then of course you can select any one of them. And this is exactly what's happening here. This is much more in the q-differentiation, much better, rather than to work with the contour, work with the function. And that's exactly what this transformation is accomplishing. So this means we get, instead of having an integral of some rational function times gamma functions over some contour that depends on stuff, we instead have insert an elliptic function which takes care of that contour. That's very important philosophical. It's not a complicated philosophical point, but very important. And so, if you have questions about it, please ask. Right. One thing that's somehow immediate, but I'm gonna run out of time today to discuss it. You see this monodrome, beautiful monodrome pictures behind me, but I'm gonna run out of time to discuss them today, which is regrettable, but nothing I can do. So this immediately gives analytic continuation and monodrome of vertex function. Right. Both from this integral and also from the actual theorem. So if you think what is this integral? In this integral, the only thing that depends there's really nothing really depends. It already gives that integral here. You think about that expression here. That's already meromorphic in all variables. That's already meromorphic continuation because precisely because I have my contour of integration is just fixed. It's just the real maximal torus inside, just the maximal compact torus inside my group. And also from this perspective here, think about this diagram. This object here, this vertex is descendants. This is a series. This object is a series in Z. So if you want that series, whereas if you go this diagram, this is analytic continuation. Because there's some, everything else is meromorphic. That makes sense. So we won't be able to talk about this today for lack of time. However, I would like to explain the main ideas of the proof of this theorem. So it's a theorem, kind of mean. Or maybe first about the gamma functions. So gamma functions. This have to do with maps from, well, I don't know, A1 or disk or whatever to X. Not that was or formal disk or whatever to the space X. Does that make sense? So because if I have, so I suppose I have some A1, you can take it formally or informally, and suppose I look at maps from A1 to A1, and let this A1, there is an action of Q here, and then this has some action of whatever you call it, W, right? So these are just polynomials, right? These are just polynomials in one variable, or whatever your field is. Polynomials 1, t squared, t cubed, and so forth. And then have weight. Well, 1 means a constant function here, so it has weight w divided by q, w divided. So the way things act on maps is that you post-compose in the target and pre-compose with the inverse in the source. So this part q squared, so on. So these are the weights. These are the weights. So these are the weights of the action. And so then means if I take the structure sheaf of that maps, this has the character, which is I have to take, I have all these functions, and so I put 1 over. So if I have a coordinate with weight w, it means I have to put w inverse here, and then 1 minus q w inverse, and then 1 minus q squared w inverse, and so forth. That makes sense? This is the character. And so this object here is nothing but the q gamma function in the variable w, right? That makes sense? This is by definition what's q gamma function. And this is much more direct than cohomology. Just so if you know the usual Iritani story, this is much more direct than the cohomology. And so in particular, if I'm interested now, if I have a you think about this, like S is let's say smooth stack. To make a smooth transition from A1 to some marginal case, let's take a smooth stack. Then if I take the character and I want to know structure shape of maps from the same A1 to S. Well, this is now some object that lives on S, if you'd like. And so then it has, since we kind of sort of like evaluation at 0 push forward. Let's take evaluation at 0 push forward of that. So this now, so if I have a map, I can evaluate it at 0. So that's a push forward. So if evaluation at 0, it's a map from this maps from A1 to S itself. So this now class that lives on S, and that class is the Q gamma function of you take the Q, because then of course the first part is that where the point goes. So this is this part here. This third thing says where 0 goes. This is first the constant term tells you where the 0 goes, and so this is already accomplished by the push forward. So then it's the rest, and then the rest is you take the rest is that is this part, and then that from that part we get the Q times the dual of the tangent bundle. This is goes in here. So where this Q gamma function we extend as multiplicative genus. Right. So if you have a map, to several, and if I have a map to product, that's going to be a product of these functions. Okay, make sense? And so now in this diagram, the gamma is maybe gamma prime is this Q gamma function of Q times T dual of X minus, since it's a stack, so this is going to be minus the dual of the Lie algebra. This is the quotient. And then since you impose the moment map equation, you think, well, maybe you also have to minus the moment map equation, but instead we put the plus Q for, maybe I'll write G star. This is for the moment map, and this has this object with the appropriate H bar. However, this acts on G star is the target of the moment map. Yes, in the target of the moment map. And the reason instead of is that we put plus instead of minus. And because it's much easier, so this is good to work with P fields. So Melissa and her students will testify it's much easier than impose equation. You introduce the dual equation to the equation. That's much better that way. And so then, of course, instead of subtracting, you add. And so that's how it works. And so and then gamma is the same same, but here instead we take with just star, no q. That q we remove, and this has to do with this, like we discussed last time, with the prime and non-prime. Would you like to cancel? Would you like to cancel with this denominator, or you don't like to cancel with this denominator? This is, yeah, we don't put that q. It's like last time. This is with the denominator 1 over h bar. So this is what it gets it up. And all right, so now my time is up, and so it's perfect time to start with the main ideas of the proof. My apologies for going over time, but there's very little choice since the year is about to end, and then maybe we'll get one more meeting this year, and then we need to take a break after that. So let's talk about the Hilbert schemes. It's already kind of interesting case. This is so we'll do it in the example of Hilbert scheme of now C2, well, in this case 5 points. So quasi maps. This is the same as PT moduli spaces. Okay. So a point in a quasi map and something like this. And so first, if I'd like to compute this, so first point, right? So this has an evaluation at infinity and evaluation at 0. And this particular point will evaluate at infinity. It will take that partition, or that partition is maybe represented by like 1 T1 inverse T1 minus T1 minus 2 T2 inverse T1 inverse T2 inverse, that sort of thing. So maybe I need to draw up like a little table here. This way we can see it more clearly. So B1 T1 inverse T1 minus 2 T2 inverse T1 inverse T2 inverse. That's what it takes at infinity. And then at 0, what was it going to look like? At 0, it's kind of the same, but it also remembers at 0, this will remember the fact that there is here it will remember the fact that there is q to the minus 3 here, and then there is q to the minus 3, q to the 3, q to the 1 here, q to the 2 here, that sort of thing. And then the first observation, so kind of the first main point, is that the weight if I take O virtual of the value of O virtual on this, and this O virtual here not symmetrized. It's not like have a not like I symmetrized. So it's not like I forgot about it. It's really not symmetrized. And so that is going to be what? This is going to be some ratio. If you take evaluation at 0 over the evaluation at infinity of some kind of gamma function expression. Depends how you want to cook. Let's say 0 infinity. Doesn't matter, since I'm not telling you what are the Q gamma expressions. So with a little difference. So this, if I'd like to compute, so this comes from where? This comes from the fact that this really comes from localization formula. Where does it come from? Localization formula says if I'd like to know T virtual, this is this is some kind of cohomology. So H naught of something minus H1 of something, and this I can compute as contribution of 0 over 1 minus Q inverse minus term at infinity over 1 minus Q inverse. Maybe this is to be absolutely consistent, that has to be multiplied by Q inverse here, but it doesn't really matter. Right? Everybody agrees? And so then if I think about what this is going to be, this will give me Q gamma functions. Clear? So if I want to write the weight of some configuration, this is written in terms of you pull back some gamma function expression from infinity, you pull back some gamma function expression from 0, and you take the ratio, because it's I mean that just comes from the fact that O virtual comes from the virtual tangent space. Virtual tangent space is some cohomology. Cohomology we can compute by localization. Localization has the form where you have a term at 0, term at infinity, subtracted, and 1 minus Q in denominator. Then if I take 1 minus Q in denominator, expand it out, I'm getting an infinite series that's going to give me a Q gamma function. Everybody, that we're on the same page here. So this means if I'd like to know if I'm free to pull back and push forward, I mean, if I'm free in this diagram, means in the diagram here, this part, this kind of edge here. So maybe I'll copy this diagram here. Means in here. means here the blue edges take care of virtual. All right, that's a good beginning, I think. Now, so point number 2. Now, when you have insertions, so if I have some elliptic function, so now let alpha be an be let alpha, maybe let gamma be an elliptic stable envelope. Some class. Then I can compare. So now we take insertions. So if I take the pullback relation by 0 gamma and compare it, take the same class relations infinity. So what's it going to be? This is going to be elliptic function, whatever, not elliptic function, section, section of some line bundle. Some line bundle, and you evaluate it at what? You'll evaluate at things like q to the minus 3 t1 inverse, t2 inverse, this sort of thing. And you divide it by the same expression. But now there is no q to the cube, right? And so there's some reason. I mean, what does it mean? Have some line bundle? There's going to be, there will be some power. So what's going to come out? This will come out. Come out things like z to the minus degree. So this is ordinary z, little z that counts degrees. Z to the minus the degree, because that minus degree is the sum of all these variables. Right. So each one of them gives me like z to the minus 3 by my. So maybe this is not minus, maybe this is plus, and then it's minus 3 the way I set it up. So the z to the minus degree, and then there's some constant, some other constant. Constant, well, means doesn't depend on z. Doesn't depend. So constant in z. Something here. Well, that constant in z, if you think about it, that constant in z, this constant z turns O virtual into O virtual hat times this h bar to the minus 1/4 dimension x. So this is the part about insertions is the part where that gives me the other ingredient in the vertex, namely we had the virtual class, and we also need the z, and z comes from this. And then the third thing, using these formulas, so using 1 and 2, we can move everything. So 1 and 2 says that if I'd like to, in my vertex, I can move everything. So what do we need? We have my have this vertex with descendants, and there's this alpha, this is beta. So then we can move it to work. We can put nothing here, just left one, and then we'll take alpha tensor like this type of beta type of thing, you know, right? Because we've instead of evaluation to infinity, we can evaluate at 0, and this is even better because that's exactly take care of the degree. And so then remains to forget about what? So to forget there's one here, somehow one plays no role, there's nothing to pull back, that the general point here, and here means on this segment, needs to be stable. Because once we have, so in other words, we have this sort of thing. This is an open set, so these are some kind of quasi maps to X, and it's some open set. These are stable locus inside the maps from my A1 to the quotient stack. Right? So quotient stack is a nice smooth stack, and then we take, well, so this maps will give the gamma functions. And so once we can put everything, instead of integrating here, we can integrate over that space, then we're done. And so then we need to show that the integral, in other words, the push forward vanishes on the complement, and then that vanishing happens in some, that is the vanishing that happens in the weak sense. So we need to extend the integration from the stable locus to the whole thing. So this is actually the hardest part. So that's so you can read on this. This is in this. You can read that part in that thing that's called this kind of inductive construction part 2. Part 2, and then you take section 3.4. So you can read that, and that requires some argument. All right, I'm 20 minutes over time now, for which I apologize. We did have an interruption in the middle, and for which I also apologize, and apologize for many other things. But that's less than I was planning to say, but that's all that I can probably be able to say today, and that's all for today, I think. Any questions?
May I ask a question? Yeah.
Yeah, go ahead, Melissa. I couldn't hear what you were saying.
Yeah, I apologize. So originally your alpha is the K-series class on the stack, and beta is a K-series class on the on X. Is that?
So on X, it really doesn't really matter if you put this. You can since X homology of X is kind of finite dimensional from the perspective we're talking about here, and so that's some finite dimensional space. You can think of that finite dimensional space and sitting well over. How it depends on the covariant variables and other variables. Maybe it's not so particularly important. In the variables xi, the variables on the stack, it's just some finite dimensional space. And so there's not so much difference there between elliptic and K-theory, because you can identify those spaces without harm.
Okay, thank you.
Yeah, thanks. So Milos is right. So one has to. In this diagram here. So what was my main diagram? Oh, sorry, I had this diagram somewhere. I lost it. So I don't know. Sorry, it's not. Oh, here, right. So here you have to say, have to be a little careful what you mean to take a churn character. But that's how the churn character will, in principle, act from. So it will take some spaces. So churn character will take some spaces of meromorphic functions, and that's and then we think of things in elliptic classes. We think of them as once we apply the churn character, we think of them as meromorphic functions that have some property, some automorphy as we change the variables by q. That's we use in the proof. We use that fact, and so then this in terms of your original space here, in terms of variables x, that's just a finite dimensional space. And so there are some, one can identify that space between K-theory and elliptic homology without too much difficulty. More questions? All right. Melissa, were you trying to ask something else? Otherwise, let's. We're in the mid-air right here, and so I propose we'll have another class on 29. I know it's not a very good day to have a class, but I also don't want to. I think it's even worse to have it in early January, and I have this class has to have at some point, has to stop at some point. So I propose I have one more meeting on the 29, and then maybe talk about the monodromy a little bit, since I already have this picture behind me, and then so then we talk about it, and then we consider, and then we say the goodbye to 2020. So thanks everybody. That will be all for today.